This is the first lecture of week 8, and in this lecture we're going to talk about the nonlinear functions of a single independent variable, specifically polynomials. So far in the lecture we only talked about cases where x and y have linear relationship and how we can estimate this relationship using OLS. But linear approximation is not always the best way or the most appropriate. There are cases when your data actually don't have a linear relationship. So in this case, in our lecture today, we're going to cover how to approximate the model when your data doesn't have a linear relationship. So going back to our example of plotting test score against student-teacher ratio, we fit this linear regression line, and it seems like the relationship between test score and student-teacher ratio can be considered as linear. However, when we look at the relationship between test score and district income, the linear line doesn't seem like it's a good approximate of the data points that we have on hand. Actually, it looks like there is a nonlinear relationship between the test score and district income. Usually, we say there is a nonlinear relationship when the slope is not constant. So in linear case, the slope is constant throughout the different points of x. But in case of nonlinear relationship, you can see that the slope is steeper in the beginning, and then later on the slope actually kind of flattens out. So in this case, we say that there's a nonlinear relationship between test score and district income. So in this lecture, we're going to look at two different approaches to modeling the nonlinear relationship. The first approach is looking at using polynomials in x variables, and second approach is using the log transformations. So the first way of approximating or modeling the nonlinear relationship is to use the polynomials in x. So for instance, we can include x plus x squared term, x cubic term, up to x to the whatever the highest order that you want to include in the model. If you look at this function, you can see that it looks pretty much like the linear multiple regression model that we have learned in the past lecture, except for the fact that regressors are now the powers of x. So this function can be estimated using our OLS. And all the different tests that we have done in OLS applies in this case as well. However, interpreting the coefficient of, say, beta 1 is a bit difficult because remember in the past lecture we said that the meaning of beta 1 is how much y changes when x changes, holding everything else constant. But in this case, we cannot really hold everything constant and just change x because everything else is a function of x. So interpreting the coefficient is not as easy as a simple linear regression model, and we're going to talk about that later. So let's go back to our example of looking at the relationship between test score and district income. In this case, variable income stands for average district income in the ith district, and it's measured in thousands of dollars per capita. We can see if the quadratic specification or cubic specification, which one is better. So in this case, in the model, we're including income square, and in the cubic specification, we're including income square as well as income to the third. So how do you estimate the quadratic specification in Stata? It's pretty simple. First, you need to create an income square variable. So the way you do that is generate average income 2. This is a variable name, by multiplying the income twice. And you just do a regress test score on the income and income square. So once you put this in Stata, you get the output that gives you the coefficient for income square term and standard error, t-statistics, and a p-value. As you can see, the p-value is way less than 0.05, meaning that it's statistically significant at 5%. So that means that the coefficient for the income squared term is statistically significant. So now we have the coefficients for the quadratic regression model from Stata. So these are the coefficients that we get from the Stata output. How do you interpret the coefficient of income? As I mentioned before, interpreting the coefficient of nonlinear regression model is a bit complicated. So the way to approach this is first you plot the data and see how it looks. So in this graph, we're plotting both the linear regression model and the quadratic regression model that we just estimated. And just by looking at it, it looks like the quadratic regression model is doing a better job fitting the data points than the linear regression model. So the second step is to compute the effects of different values of x. So in this case, let's say we want to predict the change in test score for change in district income from $5,000 per capita to $6,000 per capita. So in this case, we just plug in the number. So plug in 6 because the income variable was in thousands of dollars. We plug in 6 instead of income into the income in the above function, and then we plug in 5 and then see what the difference is, and we get 3.4. So this is saying that if the district income increases from 5,000 per capita to 6,000 per capita, the test score would increase by 3.4 points. We can do the same thing for different values of x. So as you can see in the table, you can measure how much the test score changes if the district income increases from 25,000 to 26,000 and also 45,000 to 46,000. And what you see is that the change in test score is actually decreases as the district income actually increases. So this shows that there is a nonlinear relationship, that the effect of increasing income matters more when the district income is low, but it matters less and less as the district income gets higher. So when you're in a high income district, increasing the district income by $1,000 per capita doesn't really change the test score as much as increasing the district income by 1,000 when your district income is very low. One thing to caution is not to extrapolate outside of the range, meaning that if you have data points that are, say, 5,000 to 46,000, you cannot measure how much the test score is going to change if the district income increases from 65 to 66,000 because there's no district with the 65,000 per capita income. So I want to caution you not to extrapolate outside of the data set that you have. Let's check if the cubic specification makes sense. So here we're estimating a cubic specification using Stata. Same as the quadratic specification, the first thing that you need to do is create a variable called, here in this case, we call it average income 3. That is basically an income to the third. So here we're multiplying average income times average income squared. And you run the OLS regression. you can see that the coefficient for income to the third variable has the p-value that is less than 0.05, which means that the coefficient for income to the third or cubic regressor is statistically significant, meaning that we should probably keep the cubic regressor in our model. Another way to test whether we should have a linear model or a nonlinear model is to use the f-test. So we can have a null hypothesis that says income square and income to the third coefficients are both equal to 0, which means that the linear model is correct, versus an alternative hypothesis that at least one of these coefficients is not 0. The way to test this is by typing in the command test average income 2, average income 3 in Stata, and this will carry out the f-test. We have covered this in lecture 6, week 6-2 in joint hypothesis of multiple coefficients. As you can see in Stata output, it gives you the f statistics as well as the p-value. And the p-value in this case is way less than 0.05. So we can say that we reject the null at 5% or 1% and conclude that the nonlinear model, or the model that has both or either income square and income to the third, is appropriate. So to summarize, in the case, one of the ways to model the nonlinear relationship is by using polynomials. And when you use polynomials, you can use OLS to estimate the regressors for these polynomials. The coefficients, unlike in simple linear regression, is complicated to interpret. So one way to interpret the regression function is to first plot the function and see how it fits the data, and also compute the predicted value change in y at different values of x. The way to test which order of polynomial you should estimate can be tested using the t-test or the f-test, as we have shown in the previous slides. Usually in economics data, the maximum polynomial that you probably would use is 4, meaning that the most you include in the function of nonlinear regression model is x to the 4th. And once you have that, you can test if the coefficient for x to the 4th is significant or not. And if it's significant, then you can keep all of the polynomials. But if it's not significant, then you can remove x to the 4th and then test if the coefficient for x to the 3rd, or the cubic term, is significant or not. And if it's significant, you can keep it. If it's not significant, remove it and then test x to the 2nd, and so on. So the way you decide which polynomial function to include is either by using t-test or f-test. You can also plot the data and the function to see how well the function actually fits the data. And also another way to test is you have, say, main coefficient that you're interested in. So in our case, if you're interested in, say, beta 2, and you want to include x1 to the 2nd, you can see whether including x1 to the 2nd actually changes the coefficient of beta 2, and if it does or does not, can actually impact. If it doesn't change the main coefficient, then you may not want to include. It doesn't really matter if you include the x1 to the 2nd. But if it changes, then maybe you should think about including the x1 to the second. At the end, a lot of these things are more or less a judgment call, and you may need to rely on your expertise or assumptions. So there is no right answer. There are some ways that you can see which model you should pick, but the point is that a lot of times, a lot of things are sort of based on, it's very subjective, and you just need to sort of make a decision.